All right, so we're jumping into the next bit of transformations here, and you'll notice that previously we've done this function notation where, we put our input in and it comes out and it gives us sort of two elements, and we use the dash to signify them as a transformation. So if we were thinking about two coordinates or 2 points, this is sort of the notation down here. If P has this point coordinate x, y, and we put it through this function, it can move it and give out these transformed values. Now, the linear transformation is of this form, and we actually have, this was like looking at the car, this is sort of looking at how the engine works for this particular thing, that this multiplication is how we've got things happening. So I'll explain it more with the example we've got down here, but let's just quickly go through a bit more. So we say that P has been subjected to a geometric linear transformation. So the last section was talking about what we define as a linear transformation. So we had these two sort of rules up here. So back down here. So this is sort of in our form. So this is our input value here. So maybe I should highlight so we look. So this input value here or here corresponds to this value here that goes into the function. And then this value here is our output, which corresponds to these values here. And if anything, this is realistically like the t. This is the function that actually does all the heavy lifting. And we call this the transformation matrix. So a different notation is, a lot of the time we'll write this matrix as V dash, we'll write this matrix as V and this one as A. This just allows us to show inverse operations a bit easier. So I think we've covered everything here. I've got a little note here. In this section, we're introduced to this notation for the determinant. Now, in matrices, we don't have an absolute value, or we're not looking at a modulus anymore. In vectors, we were looking at the modulus. This actually means the determinant. So let's read up on our example. So a linear transformation T has these equations. Under T, find the image of the point and the line with the equation y equals tx. So the easiest way to do this, and if we were thinking back to, and let's have a go at this. If we were thinking back to this t value here, we would have t, and in here we're putting our x and our y. So that would be the point we're putting in here, and we would be getting out, this would be given by 3, it's 3x, so it would be 3 times 3 minus y, which is minus 2, and then our other bit, sorry, I can't see the function, x plus y would be 3 plus 2. And this would give us 3 times 3 is 9, take 2, gives us 7, and we would be looking at x plus y is 5, so 3 plus 2 gives us 5. So this would be like our point here. 3 and 2 goes through this linear transformation, and it comes out a 7 and a 5. And we can, a lot of the time, use this to sort of solve different bits and pieces. But we also, and if we're going to do this in our graphics calculator, it's worth considering the matrix operations. If we wanted to find out our transformed point here, x dash y dash, what we would do is we would put this matrix in the calculator, 3, negative 1, and 1, and 1. So this I'm getting from the coefficients here, okay? And this would be times by x and y. So this would be x and y. And realistically, what we're doing here, I'm just going to copy that and paste it here so we save a little bit of writing. Okay, so what this is doing is we're putting in our coordinates here. What are we putting in? 3 and 2. 3 and 2. And this is actually a multiplication. So we would get here, so just remember that on the left hand of this equation, we've got x dash y, which is after the transformation. And we've got here, we've got a 3 times 3 plus a -1 times 2. Okay, and then we've got a 1 times 3, so 3 plus a 1 times 2, which gives us 2, which means this thing here equals 3 times 3 is 9, take 2, gives us 7 and 5. And so it gives you, here it gives you our transformed coordinates. So just sort of showing you these different things. In your graphics calculator, a lot of the time it's handy to actually save this as matrix A, and you can actually do these operations and check as you go. Now this thing here, we're looking to see how this would transform, this line would be transformed. So what we're looking at here is we need to get an X and a Y value. So we need to get this value here and this value here. Now, you'll notice in the matrix equation, we've got X here and we've got Y here, but they're not by themselves. They're not the subject of this equation. Now, we could try and rearrange them in these, but it's actually quite complex. You know, we'd be taking Y from this side and then we would have to figure out what, we'd take X from this side and then we'd have to take, add Y from this side and divide by 3, and then we'd have X and we could sub it into the other one. But we've actually got an easier way here, that because we've got our V matrix just equals our original X and Y values, and we've got V dash equals AV, what we can do here is we can go, well, let's pre-multiply by the inverse of A. So this is going to equal A inverse AV, which means we get A inverse V equals I times our V matrix. So this means that if we have this, it means that so we've got that X, Y, and now we've got, well, our inverse, remember it's going to be 1 over the determinant, and we had the determinant up here was going to be 3 times 1 minus -1 on 1, so -1 times 1, which means we're going to be looking at that's obviously going to end up being 1 over 4. And then our other value here, what do we got? We've got to remember we swap these. So remember our inverse, I'm actually skipping a step here. I probably should have done it, but let's do it. We got 1, 3, and then we end up with 1, -1. So I should have kept the formula, but I've been a bit lazy there. So X dash Y dash, and that means here we're going to have, now in the text they multiply this all together. I'm going to leave the 1/4 out the front. It just makes it a bit easier. So we're going to have, this will be X dash Y dash, X dash plus Y dash on the top element. So multiplying this row with this column, and then we're going to have -X dash plus 3Y dash. Okay, and so from this here, this means that we're going to have X, I'll write out my individual equations here. We're going to have X equals 1 on 4 X dash plus Y dash. And we're also going to have Y equals 1 on 4 -X dash plus 3Y dash. Okay, so now we've got X and Y, which was our original intention. We wanted to get them as the subject. We've now done that. So now we can sub these back in. So we get this equation. So I'm going to just use some arrows here. We're going to go, well, Y equals 2X. Take 1. Now we've got a Y value there, which was, we're going to have 1 on 4 take X dash plus 3Y dash equals, now we've got 2 times X, so we've got 2 times our X value is 1 on 4, okay, X dash plus Y dash, and then we've got minus 1. Now I'm just going to multiply everything by 4 to get rid of these denominators here. So we're going to end up with negative x dash plus 3y dash equals 2x dash plus 2y dash and then minus 4. Okay, so in this space now, we can just take 2y from both sides. So I'm going to end up with y dash here, and then I'm going to add x to both sides. So I'm going to end up with 3x dash minus 4. And that means that this function here, y equals 2x minus 1, goes into this transformation, and it comes out as y dash equals 3x dash minus 4. So that transformation, that function, it's changed this function, you know, from a slope of 2 to a slope of 3, which is pretty interesting. All right, I'm going to stop.